10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Main engines start and liftoff of the Delta II rocket with SMAC, making global observations of soil moisture for climate forecasting.
As you can see, some very, very interesting information. Oh, man. What is going on? Blair, where you been?
I missed the launch. I saw the launch, but I've got Firebird 2. The students aren't going to be able to see their data. It's going to be an academic nightmare, scientific problem. I let them down.
No, I wouldn't be that hurt over the situation. I assure you that Firebird 2 was on board. It just took off. We had separation of SMAP from the Delta II rocket, and Firebird 2, as well as the other CubeSats, will be deployed momentarily.
Now I'm perplexed because what do they have? What was I carrying? I mean, do they have backups or duplicates or parallel universes? I'm not sure. I'm a little confused right now. But
okay, well, we'll work that out shortly. But I want to know what happened to you. I want to know about your journey here.
Well, I can tell you just a few things that I recall from the trip. Let's check them out right now. It's kind of how I saw things, Franklin. It was fairly interesting, but if you're right and Firebird's still intact, then I'll feel better about things.
We're into the second half of our show. I'm glad you were able to make it here on time. And we need to start looking at the interviews and talking to the schools that were involved with the CubeSat. So you actually talked to some while you were over at Montana State.
Actually, that's true, Franklin. I had a great time with the students. And as you know, I get really into the whole college environment when I get there. But let's find out what the students had to say about their mission. Firebird 2 is launching on ELaNa 10. So I'm here at Montana State University in beautiful Bozeman, Montana, to meet the Firebird 2 team, find out all I can about their CubeSat, and who knows, maybe I can play a role in the success of their upcoming launch. Nate, can you actually tell me what Firebird stands for?
It's a lot of words. So Firebird is, it helps when I see it. Let's see, so it's a pretty intense acronym. Yeah, it's Focused Investigations of Relativistic Electron Microburst Intensity, Range, and Dynamics. And the fire and bird actually mean two separate things, where fire is the payload, where the F stands for fire, and then B, bird, is the bus. So the payload is provided by University of New Hampshire, and the bus, bird, was provided by us.
You've got like embedded acronyms, I mean, you're stacking acronyms on acronyms, and
it's like this circular acronym thing.
Is that part of the requirement when you join the team that you have to memorize that?
I don't think it's a requirement, I think it's a rite of passage.
Well, that's good. You need those are important. Yeah. What is Firebird 3 and 4? Or what are 3 and 4 Firebird?
So it's Firebird Mission 2, Flight Units 3 and 4. So it's a little bit confusing with the numerical naming system. Firebird is a constellation of two 1.5U spacecraft. Essentially what we're doing is we're measuring the relativistic electrons trapped in the inner Van Allen belts, specifically around the poles of the Earth. So essentially what happens is that electrons from the sun get trapped in the radiation belts, and what they do is they bounce back and forth really fast. And what happens is that there's this phenomenon called electron microbursts, where it's this period of very highly precipitating electrons where they terminate into the Earth. And we're trying to catch these phenomena. They're really quick, less than a second, microseconds.
Wow.
That's microbursts, really quick. So what we're doing is we're trying to measure the burst intensity, ranging, and dynamics. So essentially what happens is when our spacecraft are launched from the rocket out of a P-pod, we kind of calibrated the springs that separate the two so they separate very slowly. And we have GPS units on board. So hopefully what we're going to do is we're going to have these two units that are flying through the radiation belts, and we'll catch some activity, right? And then the second one will follow through it. Through the time and GPS data we have on board, we'll be able to figure out how long these things last, how big they are. And when these events happen, they're relatively rare as well.
You guys have a unique challenge in that you're not using a propulsion system
Yep.
So how does that work? You just take the best that you get upon launch?
It's a whole bunch of math, a whole bunch of modeling. So we spend a lot of time with software on the ground when we're designing our mission, and we're designing our various subsystems to ensure that we will be where we want to be.
What's the biggest challenge for you writing all the software for a mission of this kind?
Well, the biggest challenge with writing any software is testing it, because when you start getting into something so complex like, even a simple CubeSat, there's so many variables that, you could have this input change at one time and this input change at another time. So it's just really testing all the different cases where, if it runs fine one day, maybe it won't the next. So testing is the biggest hassle.
Now, when you encounter a bug in the software, especially in space, are you able to maybe fix it from a software standpoint?
Yeah, so there's kind of two layers of software. There's the main operating system, and then there's command sequences, which are basically commands that we can store on the spacecraft and have them execute at certain times of the day, or even when it first boots up or after a certain event has occurred. We're not able to patch the actual operating software on orbit, but we can upload new sequences so that if there's a problem, on boot, it can run a command that might fix that problem.
It's a little bit harder to fix things in space, I would imagine.
It is, yeah, and it comes back to the same thing. You have to test the software patches before you release them, because maybe this spacecraft's not working quite how you want it, but this patch might kill it. With the first two Firebird units that launched about a year ago, we had the engineering development unit here on the ground. And now that engineering development unit is going to be launching into space with another Firebird this time. But we still have a little bit of hardware left here on the ground that we can test with and test any changes to the spacecraft software.
What goes into a decision to build your own board? Do you usually do that because it's an opportunity for you to try something, or is it dissatisfaction with what you were able to get and you're kind of like honing it?
So essentially, originally our first spacecraft, Merope, launched in 2006, made a big crater in Kazakhstan. And that mission, we designed everything. I wasn't here at that time, but we designed everything. Same thing for Herbie that launched in 2011. We designed every single thing. But for Firebird, we decided to sort of branch out and focus on what we wanted to design. So there's an optimization problem, trying to see what we want to purchase commercial off the shelf and what we want to design. Specifically for the power board, we were not satisfied with its performance. It did not perform how we expected it to. So we designed our own because we could not rely on the power board we were using previously.
What kind of challenges do you face putting together a power system for one of these CubeSats?
Well, the big thing about the power system is you're sort of kind of the heart and soul of the spacecraft, where, maybe the flight computer's the brain, the chassis of the structure is the skeleton. The power system has to distribute all the power to all the different components in the spacecraft, and all that power has to be consistent to everything. So it's a really big challenge to make sure that the batteries are properly sourcing the power, properly getting charged by the solar panels, and there's no break in the loop. And then you got to be careful that you're not going to discharge the batteries below a certain point, so they're going to, be in a broken state on orbit.
Heat can be a real problem on the spacecraft. What are some of the things that you did to help dissipate the heat problem? Because I always thought the heat problem would be something from the sun, but there's some heat problems on how from the instruments itself and things like that. So how do you handle those problems in space?
We have a few small components that actually generate quite a lot of heat. So we have to basically get that from inside the spacecraft outside of the spacecraft. And so we have to figure out either conductively or radiation. Turns out you just paint it a certain color. And that's what you paint it black, basically, is what it comes down to.
Awesome.
And that helps the radiation.
So how do you determine what's causing heat in space? Like if your one hasn't launched yet, is that in some of your testing that you do here in the
so we
lab?
have a thermal vacuum chamber just over there. And so we do a lot of testing in there. And we can get it cold, we can get it hot. And in vacuum, we can test how well the spacecraft will shed the heat.
Are there some structures that are just better at reducing heat than others? And did you consider even making the spacecraft out of a different material at any point?
We didn't have that much design freedom, unfortunately. Aluminum is pretty good. Aluminum is one of the best, and that's what it's made out of. But at the time, we had to get it delivered quickly, so we didn't have time to make drastic changes like that.
Well, now, listen, I'm looking at this CubeSat, and it's very similar looking to the Tesseract.
I don't know what that is.
You don't know what the Tesseract is?
No.
Tesseract.
I'm not sure what a Tesseract is, my name.
It was in the Avengers, the device that opened the portal to Asgard.
Oh, yeah. No, I think that's coincidental.
It's coincidental,
Yeah.
okay. And so there's no danger of this opening a portal and perhaps bringing about our doom.
We could be, I hope not. I'm not sure.
I hope not. Well, of the Avengers, who do you think would be more inclined to build a CubeSat of the Avengers that you know of?
Iron Man.
Yeah,
I would probably go with Iron Man.
Probably Iron Man.
Iron Man.
Yeah.
Okay. It's got the whole Stark Industries.
Yeah.
I wonder if Stark Industries has a CubeSat department.
I don't know.
Originally, our first spacecraft, Merope, launched in 2006. Made a big crater in Kazakhstan.
So, we found it.
Apart from not really understanding the whole Avengers mythology, the students are a really bright group. The real question is, how can I convince Dave Klumpar that I have the enthusiasm it takes to be a member of this program? It's really important that I make a very good impression on Dave Klumpar, the principal investigator for Firebird, if I want to be a valuable member of this team.
Well, Blair, being enthusiastic and gung-ho is certainly a part of being a good member of the team, but there's a lot more to being a rocket scientist than just dressing for the cause.
I mean, this really reflects, this is natural for me. I feel completely comfortable and ready to support Firebird and the entire team with my MSU get-up.
It's a great start.
What I want to know is, if I'm going to be a member of this team, tell me a little bit about how Montana State, and you in particular, got involved in CubeSats, because this is a really growing industry.
It wasn't a growing industry at the time, 14 years ago, but I had a 40-year career doing space science research. I started that career as a sophomore in college building space flight hardware. And I wanted to come to an institution like Montana State and give our students, these students, the current day students, that kind of experience at building small satellites. Big satellites are hard and costly to build. Small satellites, you can build them for a finite amount of money.
It's still the same process, and it still requires a lot of the same skills. You do get a lot from going through a program like that.
Yeah, and in effect, not only the skills, all of the subsystems, all of the functionality of a spacecraft is the same irrespective of its size. It needs a power system, it needs a brain, it needs the heart, it needs communications link. So whether it's Hubble Space Telescope or a 3U CubeSat, it's the same amount of stuff. And most of the things that can go wrong, if they break something, if they let the smoke out of a board, we get a lot of blue smoke in the room when they hook up the wires wrong. But as part of the learning process and understanding how those mistakes can be corrected and not happen,
Well, now you have 2 satellites flying for Firebird already that have been successful, even with the challenges that they faced, and you're about to launch 2 more. What's next on the horizon for MSU?
We're really interested in achieving 3 different goals. We want to train students, experiential training in how to be space engineers and space scientists. We want to do science in space, hence a Firebird type mission. We're also interested in building on the technologies to make these very small satellites much more capable. And yes, we're finding that we want to get to larger and larger sizes too. So 1U, 3Us, and now we're working in the 6U regime.
Now on the 6U, is the primary motivation to expand to 6U really so you can do more science, or is it also related to things like maybe being able to add propulsion or some other capability?
We want to get more power, and surface area gets us more solar arrays, more solar panels, more solar cells. It gets us more power, and we can put more capability into a box that's a little bit larger. For example, we have a proposal in right now to fly a CubeSat into an orbit around the sun, and it's going to carry a laser communication system. That takes a little more space than a standard RF radio
Now,
transmitter.
a CubeSat around the sun, did I hear that correctly?
That's right.
Well, now how would you, and we're speaking very enthusiastically clad layman's terms here, but how are you going to get your CubeSat to the sun without a major propulsion system?
Well, you know, NASA's developing the next large launch vehicle, the Space Launch System. And NASA has agreed to allow secondary payloads to ride along on what's called the EM1 flight in 2017 or 2018. And those satellites will be carried into an orbit that places them past the moon and into an orbit around the sun. So even without propulsion on the satellite, it's the big rocket booster that's going to get us on the right trajectory.
Well, that would be
Pretty
something.
cool opportunity.
Yeah, I'm really thinking, because I'm a big fan of space weather, not terrible space weather, but good, healthy space weather. And so I could see a lot of opportunities where perhaps I could play a role on the team.
I'll bet that we could get you on this team if you can do more one-arm push-ups against our sports champ out on the field at homecoming this weekend. You'll become a member of our Space Science and Engineering Lab team.
Well, that's quite a challenge there, because I can't do 2-hand push-ups. I mean, I got to get in shape to do those. So, I'll work on it, okay?
Yeah.
Because I want to be a part of the team any way you see fit. I want to try it because obviously you guys are doing some great work, and if I can be a part of it, all the better.
And I'll give you $10 if you beat champ.
Okay. All right. Joining us now is Alex Saunders, who is a student at Cal Poly. Thanks for being on the show with us.
Oh, thanks. It's great to be here. Now, I heard you had a bet with Montana. Who could do the most push-ups?
Yeah, I did, actually. That's true. And we didn't get to follow through on the bet, but I'm sure I could crush him in a one-arm push-up competition because I'm pretty good.
All right. Well, I have some money riding on that. So.
Okay, well, if we resolve that, we'll have to settle up. Anyway, what we're here to talk about now is ExoCube, which I believe is the CubeSat that's launching for Cal Poly, and I'm not sure. I think you guys are the last to deploy today. Is that right?
Yeah, we'll be the last out of our P-pod.
Okay, well, tell us, what is ExoCube?
So ExoCube is a weather satellite that we've been working on at Cal Poly. It's measuring hydrogen, oxygen, helium, and nitrogen, ions and neutrals in the exosphere, which haven't been measured in a while in the exosphere. So.
And that's basically for space weather, correct?
Yes, and also ion storms, possibly when you get a solar flare, and then the ions that occur during that in the exosphere.
Gotcha. Now, your role on ExoCube, what did you do in working on ExoCube?
So I was an electronics engineer. I designed a lot of our sensors interface and interface with the Goddard instrument, the mass spectrometer.
Did you say NASA Goddard?
Yes.
So you were actually working on something that they would use, or what was the relationship with Goddard?
We needed an instrument, and this was sponsored by the NSF, and looking for a mass spectrometer, but mass spectrometers are normally very large, so we had to miniaturize it. So NASA Goddard said, hey, we can miniaturize it. So then they built us a miniaturized mass spectrometer. And so we had to communicate with them, to interface with them, and say, okay, how are we going to talk to you? How are we going to get your data? So we've got to work closely with them.
This is one of the things that I think is so great about the whole ELaNa program is not only do you get to build satellites, but you really go through that entire process of working with other organizations and institutions to, get payload, to get instruments, things like that, because it's really a cool thing.
Oh, it really is. Got to, talk with them. They're a professional organization. We're students, so as we're going through, we're getting advice from them as well on how maybe we can improve. So it's pretty awesome.
We're back in the lab with Keith Mashburn, the research engineer here at Montana State University. Keith, what are some of the things that you're seeing in the CubeSat world that are actually going to help the students in the next few years?
Well, I would say I think one of the most disruptive new methodologies is the advent of using additive manufacturing in building satellites, or 3D printing as it's more traditionally known. And it's a much more diverse than, say, trying to build something purely out of metal, where you're restricted to standard processes, standard materials. And with the additive manufacturing, you can build structures that you cannot make using more traditional manufacturing methods.
So looking into the future for Montana State and the projects they have here, is your next satellite going to be done through additive manufacturing, or will that be several satellites down the line?
Well, I think we're already really setting the tone for our next generation of small satellites with our PrintSat mission, which is actually a 3D printing based satellite structure with all your standard avionics systems inside of it. But what I would really like to see is our next generation satellites utilizing additive manufacturing to the greatest extent possible, because of the wonderful advances and the savings in time and assembly. One of the greatest advantages, I think, of additive manufacturing is you can build these complex assemblies with very few fasteners. And as a guy who spends most of his day putting the spacecraft together, anything you can do to reduce part counts, to reduce complexity, will save us all time and money in the end.
How would 3D printing have helped, or additive manufacturing have helped assemble a mission like Firebird?
Well, I'll just say that access is a problem. Depending on the levels of assembly, you can only do certain things at certain times. And so you really have to plan out the assembly in exquisite detail. And in some cases, certain operations are impeded by a week, a few days, while you wait on epoxy to dry because you can't bolt this next thing together. And so by using additive manufacturing, I think we could greatly simplify the assembly process and reduce the overall build time substantially. And I think for us, that would be a wonderful benefit.
Well, I see a lot of advances coming your way for CubeSats. It's very exciting. Hopefully, when I'm fully adopted as a team member, you will have a sort of a foolproof CubeSat structure that I can't damage, and we can possibly launch a successful CubeSat together if I can get on board here.
That sounds like a great idea.
I appreciate it. I'm going to do everything I can to prove that I'm qualified. It was awesome to spend time with the Firebird 2 team here at Montana State University, but I'm not quite sure I've done enough to be a valued part of this team. If only I could find a way.
We will very carefully package the spacecraft, put them inside this box, and ship them off to Vandenberg Air Force Base.
Spacecraft in there?
That's correct.
Fantastic. Firebird on the move. Firebird on the move. Satellites in hand. It's Vandenberg or bust. Let's go. All right. I'm going to be a part of the team. Spin move. Watch out. Little side step. Nice. But just looking at that video, I'm sitting there thinking, I look so young. I feel like I'm so much older now after that. But thanks for being on the show with us. We do want to talk about GRIFX, but just to let everyone know, during our interview here, we're actually going to get word from someone just off camera that the deployments are going well. So Charles, tell us a little bit about GRIFX.
Well, GRIFX is a technology validation mission that's sponsored by our NASA's Earth Science Technology Office. And what we're doing is we're flying a very, very high-speed camera that will be used to help us understand atmospheric chemistry and pollution transport from GEO. And we want to ensure that the camera works properly in space. And it will be part of a mission. Sounds like Firebird just deployed.
I was going to say, I'm very interested in the science of GRIFX, but we got audible celebration from the control room. It's really good to know that Firebird is out. They're very excited.
It's very exciting.
And you're on deck now.
We're looking forward to going next. Yes.
A little more stressful?
No, not stressful, just very excited.
Yeah.
And we're really looking forward to our safe deployment and starting operations. As I was briefly saying, it's going to support an instrument called the Panchromatic Fourier Transform Spectrometer.
I'm so glad you said that, because I tried earlier and it wasn't working too well.
It's a mouthful, yes, exactly.
Yeah, well, tell us, you said this was part of a camera?
Yes.
Now, will that provide images, like photo quality images, or are these scientific images?
Yes, it will provide scientific imagery. In fact, this is a copy, or an engineering sample of the device that we're flying. And what it is called a ROIC, or Readout Integrated Circuit. And it takes a very high frame rate imagery, and that will allow us to make these future measurements as part of the Pan-FTS instrument.
Now, so...
sounds like GRIFX has deployed.
Yes, you're good.
Yes. And our collaborators at University of Michigan, I'm sure, are very proud as well, as we are at JPL.
I was going to ask you whether the pan,
yes.
whether it was actually, that's already been validated, or is that actually what's being tested on this flight?
Oh, yes. Well, we're testing this ROIC chip on this flight, and once we can verify that it's working well, we'll integrate it into the Pan-FTS instrument, which we hope to finish for a future mission. So by doing this flight, we'll learn a lot, and it will benefit all types of missions going forward.
Yeah, and the third and final CubeSat has been deployed, and it's a success, so that's really great.
That's great news.
We heard cheers slightly off camera in the other room, but tell us, how's the mood? How's everybody feeling after a successful deployment?
I think we're relieved. I don't know how else to describe it. It's been a long road. We've been working on this mission for about 18 months to bring everything together, and it always feels good to finally put the spacecraft where they belong. Now, the real work begins for the CubeSat teams. They have to go perform their mission. We go home and get ready for the next launch.
Yeah, well, I tell you, I'm proud of these kids, and whenever you talk to the students, and realize that you're talking to college students that are building satellites, and that's such a great resume builder for them. But then it's also a big benefit for NASA and other folks that are getting to launch missions on a much smaller scale. Tell us a little bit about the success that we have on this mission.
Absolutely. Well, let's see. There are several tangible benefits that the taxpayers get from missions like these. First of all, we are encouraging the next generation of scientists and engineers to go out and do great things, and we've been talking all about that today. These students are a great example of that, and there's many, many more behind the scenes. These are just the representatives for those teams, but there are a lot of others that have helped make this happen. That's a huge thing. The second thing is where you get to go demonstrate technology. GRIFX is a great example of that. This is a way to buy down risk on more expensive missions in the future. These CubeSats are relatively inexpensive, certainly order of magnitude or two less than what we would see for the large spacecraft that GRIFX will ultimately, that instrument will be involved with. So, that's a big thing. And then thirdly, scientific return. We're all interested in broadening man's depth of scientific knowledge, and these missions are doing real science in space. And so for a relatively inexpensive price, we get some interesting science return as well.
That's what I think is really interesting, that it's providing a real economical way to get real data in space. As you know, I tried to put together my own CubeSat.
I remember that.
I wasn't as successful as others, but
no, you weren't.
But nonetheless, it seems to me that we're seeing a lot of benefits in a lot of areas. So it's like you've got industry benefits, NASA benefits, educational institutions benefits. It's like a win-win-win.
Win cubed.
Nice. It's almost like he planned it. Anyway, you're watching NASA Edge, an inside and outside look at all things NASA.